trying to be. You are trying to be. Yeah. I don't blame you. Oh.
I don't even know whether it's working.
Oh, that is not right.
It's dodgy, isn't it?
Have they not changed it?
They've
They've still not changed it on the registers. Go tell the woman.
Oh,
Is it not just because you all print off the same one?
sorry, I need to change it. I'll change it on the registers.
Thank you. I'm going to be that.
Okay, chapter 10. That's very exciting.
No. No, it's not.
I think we have different things that are exciting.
I am excited. It's called normal subgroups. And factor groups. Can't see much of it.
Yeah, I like the bit that I can see.
Oh, you can
I like that too.
see what one of them.
It's a good combo.
Like a jumper too. Okay, let's stop this. Okay, this is already on. This is already on the recording. So, okay, normal subgroups and factor groups. Okay, so there's. Oh, this is called 10.1. I've got a little bit too excited. Okay.
I mean, it's both really.
A. Normal subgroups.
What is normal?
Yes, I'm just about to say. Okay, so for a little while, let's just look at what a normal subgroup is, and in a little bit, it will become clear why a normal subgroup is an important thing. Okay, but you have to have some patience, because before we get to actually saying what they're good for, we need to have a look at what they are. So the definition. But I won't start by a definition. I will start by theorem. I'll do it slightly differently to what the book does. So I'll start by theorem 10.3. And theorem 10.3 says that let G be a group and H a subgroup of G. Then the following are equivalent. For every element of G, the left coset, is this called the left coset? I think this is called the left coset.
Yeah.
Is the same as the right coset. Okay. Number 2. For every element of G, when you do G times H times G inverse, this is called a conjugate of the subgroup H. As Killian told you about conjugates. If not, then he'll tell them about them later. But so this, whatever it's called, GHG inverse, is a subset or a subgroup, if you like, of H. Okay, so when you take all the elements of H and you multiply them by G from the left and G inverse from the right, you always only end up with elements in H. Okay, you can't ever jump out. That's the second condition. And the third condition is that this is not only a subset, but it's actually equal to H. Okay? So this means that not only you can't jump out, but you cover everything in H. theorem.
I'm using my ruler as a bookmark.
Okay. Can't remember the proof, so I need to.
We just trust you.
Yes. It's probably in the book.
It is on the book.
So what do we need to show? We need to show that given 1, we can prove 2. So suppose G being G and little h in the subgroup, and then what we want to show that if we want that G H G inverse is in H. Okay. So if showing that something is a subset means you take any element here. Well, the elements here are exactly all these, where H runs through all the elements of big H. And we want to show that when you take any element there, it is also an element there. That's what being a subset means. And so that's what we want. It's good to know what we want, but it's also good to know what we know. So what do we know? We know that G times big H is equal to H times G. So what does that mean? It means that there exists some H dash in the subgroup such that when I look at this G and H that I have, G times H is equal to H dash times G. It's so much. Okay, that's we know this. Well, what does this mean? This means that if I take G and a little h, then it's going to be some other, possibly some other little h times G. Because it has to be in this place. Okay. Not necessarily the same h. So it's not necessarily true that G times h is equal to h times G for any elements, but if you go through all of them in the subgroup, you're getting all of them in this subgroup. Yeah, sorry, in this subgroup, and yeah, again, if you go through all little h's in this subgroup, the things you're getting in the coset are exactly the same things that you're getting when you go with h in this subgroup and you're doing the multiplication the other way around, but not necessarily in the same order. Okay? They can be shuffled up. So it can be some other h dash, which does the trick, and then this is equal to h dash g g inverse, which is h dash, which is in h. So that's what we wanted.
Exciting.
It is, but students falling asleep in the lecture is not really making my job any easier.
No, that's
Not yet.
No.
Okay. More excitement. Okay. So again, we take an element of G. We know that G, H, G inverse is a subset of H. We want to show equality, so we want to show that they're also subset in the opposite direction. So H is a subset of G, H, G inverse. Okay, so So we look at any element of H and we want to show that it's in the other set because that's what it means to be a subset. And the second condition gives us, but applied to G inverse, we have that if you take G inverse H, G, that's in H. So G inverse H, G inverse is in G, H, G inverse. Is it still making any sense? So this is an H, in brackets, so there. And so this is equal to what? H. Because they munch each other, on the left of H.
Did you say they munch each other?
Yes. Cannibalism. Okay, so the last thing is that 3 implies 1. I hope you know from your 2 years at university that if you have following or equivalent, you probably know that from Killian.
Actually, I've never seen that. If they just writes it.
Okay, so now you've seen that.
He writes the word. Too much.
Okay. It starts in a very exciting way. So what do we, well, what is 1? 1 means that the left coset is the same as the right coset. One way of doing proofs that 2 sets are equal, quite a common way, is that you show that one is the subset, one is a subset of the other, and the other is a subset of the one. Okay? You show them both ways, and that shows that they're equal sets.
Yes.
So first, we want that GH is a subset of HG. So let H be some element of H. And we want to show that G times H, so little g times little h, is in HG. Right? So what is GHG inverse? Yes. Now, where's H from? H is from H, so it's from here as well. So it has to be able to. We have to be able to write it in the form G, some other H, G inverse. Okay. So there exists something in H such that our chosen H is G, that other H, G inverse. Where am I? And hence, what have I done? Oh yeah, GH equals HG. So this is in HG.
Wait, should that not be? Should
Yes.
they not be the other way around? Should it not be HD is G, H down? So it
Yeah.
post multiplied by G to get rid of the G inverse.
Yes.
So yeah.
You're absolutely right. Thank you. So what I'm going to do is slightly different. Well, what I need to do is actually write in my notes, but copied it wrong. So, I mean, okay, it's a different argument, but it's the same thing. So H is in H. So when I put it into this formula, GH, G inverse, I get something in the subgroup H, and I call this something H dash. Okay?
I like that, that's fair.
Slightly different to what it was before. Now it works. So H dash is this, and now when I times it by G, or that, cancel the G inverse on the right, I get, we can't cancel. So yeah, if you multiply it by G from the right, you get this, and therefore GH is in this cosine. Okay, so therefore this coset is a subset of this coset, and the other conclusion is proved wirelessly. I can't say it, and I can't even write it properly.
It's just to say analogous.
Yeah.
Analogous,
Okay.
yeah.
Analogous.
Analogous.
Okay, which means that the proof is the same, except it's only similar. Okay.
Just like, yeah, there are too many G's and H's.
Oh, sorry. Everybody says H.
You have to look at.
Everybody okay with that?
Yeah.
Okay.
Yeah.
Everybody.
Everyone's fine.
It's gone now.
This is why I don't write it down when you say it, because I will never understand what you're saying.
Definition.
Hey.
A subgroup H that satisfies these conditions you've studied it before.
I looked in the book.
Is called a. I know.
Oh, exciting blue pen.
Subgroup of G. Okay, people complain that they can't see the blue. I need to use it.
Oh, whoa, no, I don't like that. Oh, oh no.
A highlighter. I was asked to use a highlighter.
Danny, can you see that?
See what?
It's a different colour.
Yeah. I mean, I can see it for the highlight. So
So why did you ask for the
there's a
highlighter?
bloody red and green pens in that one the other week. They
I
all
thought it
look
was
like that.
orange, you couldn't see.
Okay.
Orange is formed between red and green.
So I'll stop using the highlights now.
Yeah.
Just keep it blue. Okay, so now we know what the normal subgroup is. Okay, so notation is
Ooh,
triangular lesson.
that's a bit weird.
And also one says that H is normal in G. Okay, example 10.1, silly. But it's not so silly. So, right, okay. You're reading the book, so you know it, but in an abelian group, what are the normal subgroups?
All of
All the
Any subgroup is normal. Why is that?
for it to be abelian, it has to be. Oh, GH.
Commutative.
Yeah.
So for any G and H, GH equals HG, even element-wise. So oh,
I see why it's so.
for any subgroup. That's what I think. Actually, what I said before was that they don't have to be the same element one by one, but in an abelian group, they actually are the same elements one by one. So the cosets are always the same. Example 1099. It's not in the book, so I can give it any number.
Write it down.
In any G, there are always two normal subgroups. Well, this E subgroup, its cosets are all the one element subsets of G, so they're the same left or right. And of G, there's only one coset, so that's the same left or right. Now, some non-examples. So when you look at the group S3, that's the symmetric group on three elements, so all permutations of 1, 2, 3. Subgroup which only has the identity and one transposition. So if I take the element called 1, 2, 3, so this three cycle 1, 2, 3. What is 1, 2, 3 times H? What's the coset of 1, 2, 3?
1, 2, 3.
You're too quick.
Okay.
Okay, so 1, 2, 3 times the identity is 1, 2, 3. And 1, 2, 3 composed with 1, 2 is 1 goes to 2, goes to 3. So 1 goes to 3. And 3 goes to 1. And 2 goes to 2. Okay. So you get these two elements in the coset, and if you do it from the other side, then you get 1, 2, 3 again, but 1, 2 followed by 1, 2, 3 is well after. Killin's after. Well, 1 goes to 2, goes to 1, so 1 goes to 1. 2 goes to 3 and stays there, so 2 goes to 3, and 3 goes to 1 goes to 2, so you get 2, 3. So they're not equal. And therefore, this H is not normal. So it makes sense, actually. Now we actually see that. It makes sense to define what a normal subgroup is, because there are some subgroups that don't satisfy these conditions. Well, probably all of them. Okay, and second example, I'll call it N for some reason. So N is yeah, I'll call it N because I want to be consistent with the book. So when you're doing your internal student survey, you can write that N is always consistent with the book, except when he starts with a theorem and doesn't give the definition of a normal subgroup. Then writes a very different definition of a normal subgroup than the book does, but it's a better definition.
It's not different.
What? Okay.
Your definition is not different.
It is. It is not.
No.
Because they changed it. No. It's easy.
No, it's not.
Okay. So this. So how many? So okay. What's the index? Do you remember the index of a subgroup?
I remember that notation.
Now, this is the number of cosets. But there was a theorem. Oh, there was a theorem. And thereabouts where there was the Lagrange theorem, wasn't there? That the order of a subgroup always divides.
Yeah.
Yeah, and the ratio or the result is called the index, and it's the number of cosets. So in this case, well, we're looking at S3. We know this has 3 factorial. That's 6 elements, and N has 3 elements. So there are 2 cosets. Okay, the first coset that's easy. That's just N. And the other coset is, well, what have we not got? 1, 2, 1, 3, 2, 3. So that's any of them will do. So these are the left cosets, but they're also the right cosets because how could it not be? Okay, so this is normal. And in fact, I mean, kind of this is at the heart of the argument that if the index of a subgroup is 2, it's always normal. the index of H in G. Any questions about these things? It's all good. B. Okay, so this is, now we're coming to why normal subgroups are good and what they're useful for. So this theorem is also a definition, but it's called a theorem. And it starts by saying that we have a normal subgroup I think I'm going home. Define an operation on the cosets of n. Okay. So what is a coset? It's some sort of an. Okay. And I have another coset which I call bn. And the operation gives me coset, which is the coset of AB. Then the set of all cosets with this operation is a flying circus.
That's
No.
not true.
It's a group. It's a group, sorry. Anything wrong? It's a group.
Yeah.
I'll sit next to you next time.
It's called this. And its order is equal to the index of n in G. It's a group.
So,
Yes.
wait.
I'm waiting.
I'm confused.
Yes, that's fine.
So the operation is it basically if that operation is true? Don't understand.
Okay.
I need to scribble that through. But is it always gonna? Is A and Bn always gonna equal ABn? I don't know. That's what.
No, that's the definition.
That's
No, yeah.
yeah, but
Right? You get a coset. It's
Yeah. Yeah.
It's a coset of A. You get a coset which contains B. So you operate, and I define the result to be the coset that contains AB. Okay. I think your question is, even though you've not said it, is if I take a different A from the same coset and a different B from the same coset, am I going to get the same result? Yeah. Okay. Proof. Is it even an operation?
That's what. Yeah. Is it? Well, I'm just confused.
No.
And then I don't understand it. About it being a group.
Okay, what? About it being a group. Okay, so so we have so the elements of something are the cosets. Okay? If I get two cosets, I can times them. How I do it? I pick one element from one coset, another element from the other coset. I times them in the group. And then I give you the coset of the result. Okay, that's what this means. Now, of course, you get two cosets. They're sets. Okay? You pick a different A than I did. You pick a different B than I did. You times them, and you get the coset of the result. Is it always going to be the same thing? Are we going to get the same result, no matter which one we pick out? That's the question. Okay, so suppose we have a coset and we have another coset which can be described by two different A's, and the other one is described by two different B's. Yeah, so Kim and I have two cosets.
Okay.
Okay, and we want to know if we do this operation on them, what do we get? Okay, so I take A1 from the first coset and B1 from second coset. Kim takes A2 from the first coset and B2 from the second coset. Are we going to get the same thing? Well, so
How A1 from the same coset, they have A2 from the same coset.
say it again.
Why A1 from the same coset is equal to A2 from the same coset?
Oh, because I tell you so. No, this is what we're starting with. Okay, we get a coset. So it's a coset of A1, but it's also a coset of A2. It's a coset of anything that is in it. And there's another coset. And you want to know what the result of the operation is on the two cosets. So what we're trying to say is that it doesn't matter which A I pick from the first, and it doesn't matter which B I pick from the second. I always get the same results. Okay? And so what I'm doing is, if I pick two different A's from the first one and two different B's from the second one, do they give me the same result? Okay, that's what we're asking now. We've not answered it yet, but that's what we want. We want that the coset of A1, B1 is the same as the coset of A2, B2. Okay, and now the A1 is in this coset, which is also this coset, and therefore there exists some M in this normal subgroup such that A1 equals A2 times M, because A1 is in A2M. Yes.
Sorry. Wait. Would it not be like A1, like little M? What to A1? My brain's
No, it
just
wouldn't.
confused. Okay.
And B1 is in B1N, which is equal to B2N by our assumption. And therefore, if B1 is in B2N, we have to be able to write it as some B2N. Do you now know what you mean?
Or I feel like I've misunderstood the definition of a coset if we're saying that A1 belongs to A1N. Because I thought A1, like when you define a coset like that, where you have like little GH, G is like the...
G you fix.
Yeah. But it doesn't necessarily belong in the coset. Because,
Oh, it does, because the identity belongs to any subgroup.
but we're not
That's
talking
the
about
identity.
subgroups.
Yes, we are, and it's a normal
Cosets.
subgroup. I know.
Wait,
Okay.
hang on. And it's, but I thought this was, we were talking about cosets.
Yes, we are talking about cosets. Indeed.
So then,
But the coset is G
Oh wait, hang on. No, I'm with you. Because E is in N.
Yes,
So then
E
you
is in N.
multiply A1 by E.
Yes.
So A1 would belong to the coset.
So if you have G times
Okay.
H as a coset, then G is in that coset and not any other.
Yeah.
Okay.
I don't know why. Yeah. Okay. Sorry. I was doing so well up until about 5 minutes ago.
Okay, now, quick. I have a decision in 5 minutes.
Okay. Sorry.
No, 15. So this, what's this? So what's A1? A1 is A to M.
Mhm.
What's B1? It's B to N times N. Okay?
Mm.
Now, by the rules of cosetting, you get A to M, B to N. Well, because N is in N, so if I do N times anything in N, I'm not getting out of N. Okay, so what I'm
Yeah. I'll accept that.
The topic of math is clearly important.
Danny, you weren't in. Don't understand. You actually.
I wasn't there.
now B to N is NB2. Why?
Because we're in a normal group.
Yes, because N is normal.
Understood that bit.
Now, what is MN?
N belongs to N.
Yeah,
you've
so
not
what
like
is
them.
N times N?
N.
Yes. So what's this?
A2, B2 then.
Why is that?
Because we're in a normal thing. Okay. But then the bit about it being a group.
Then you do the rest.
Now, is it a group?
No.
Why not?
I mean, it could.
Should be a group.
Should it?
Yes. So that's like it is. That's like a spoiler because we'll do that tomorrow. Because
Oh, yeah.
Like, it's like this.
Behind every line.
it's a cliffhanger end.
I'm in theory as well.
Okay, so the great question that Kim had, we've answered. The operation actually works, so it doesn't matter which A and which B we pick. We always are getting the same result. Yeah? If we pick my A and B and do the coset, we get the same result as if we pick Kim's A and B or Miriam's A and B. That would be H and B3, but doesn't matter. Okay.
Okay.
That we know.
Yeah.
Now there are still things to prove really that it's a group and it has that order. Well, the order is simple because there are as many cosets as that thing, and the group is not too hard, so we'll just quickly do it tomorrow. Goodbye.
Still skeptical about it being a group.